Hello my dear children of class 12 science. Today again we do continue with the chapter that we had already started in the last class. The chapter name is semiconductor devices or electronics. Okay, so this is one of the first chapter under unit number 9. Okay, and in today's class we do continue with the topic called energy band diagram in semiconductor. Because in the last class, if you remember, we had done up to energy band diagram in case of conductor. Okay. Now similarly, there is another substance whose conductivity lies between conductor and insulator. Okay. And that particular substance is called semiconductor. So you know what is semiconductor? What are the examples of semiconductor? Now we just try to understand what is the energy band diagram of semiconductor. Basically in semiconductor, okay, the energy gap between conduction band, you can see this is a conduction band, okay, and there's a valence band. Okay, conduction band and valence band energy gap is less as compared to insulator. Okay, okay, and that energy gap, this energy gap, okay, that is Eg, I'm writing noise, will be less than 3 electron volt. How much electron volt? 3 electron volt. So that means conduction band lies just at certain distance above the valence band. Okay, so that the energy gap between the conduction band and valence band is nearly how much? Less than how much? 3 electron volt. Now you know there are the example of semiconductor like carbon, silicon, germanium. Okay, so out of this semiconductor, example of semiconductor, as you know, silicon and germanium are the most commonly used semiconductors, and their energy gap is nothing but in the range of 1.1 electron volt and 0.7 electron volt. That means silicon has energy gap of 1.1 electron volt, okay, and germanium has energy gap how much? 0.7 electron volt. But normally for the semiconductor, the energy gap, okay, will be less than 3 electron volt. And normally at a very low temperature, okay, the semiconductor conduction valence band is completely filled. Okay, the valence band is completely filled where conduction band is empty. Okay, so when the semiconductor is not at room temperature, semiconductor is at a temperature less than room temperature, okay, then the valence band is completely filled, okay, whereas the conduction band is empty. But if I take a semiconductor which is at room temperature, so let me just take the example of semiconductor like silicon. So now for that, let me just draw it. This is for any semiconductor. This is for any semiconductor, okay, conductor at a temperature less than at less than room temperature. At what temperature? Less than what temperature? Room temperature. But we can take the semiconductor at room temperature also. So let me just take the example of silicon. Okay, so let me just draw the diagram. Okay, let me just draw the diagram. Okay, now this is a valence band and this is a conduction band. Okay, now for silicon, your energy gap is 1.1 electron volt. See, as I said, silicon has energy gap 1.1 electron volt. Now this is at room temperatures. Let me just take, say silicon is at what temperature? Room temperature. Silicon at room temperature. So at room temperature, the valence band, which is completely filled, but the conduction band will be partially filled. Means few of the electrons, okay, can move from valence band to the which band? Conduction band. So at room temperature, okay, when the silicon, if you take the semiconductor like silicon at room temperature, then what happen? At room temperature, few of its electrons in the valence band, few of its electrons in the which band? Valence band, okay, have sufficient energy. Have what? Sufficient what energy? Kinetic energy of thermal motion of the electrons, okay, to cross from the energy gap, from this energy gap of 1.1 electron volt into the conduction band. That means very few of the electrons, okay, can move from valence band to which band? Conduction band, by getting sufficient amount of what energy? Kinetic energy, okay, so that this energy which is received by this electron from valence band will be more than the energy gap, okay, so that they can cross from valence band to which band? Conduction band. Okay, but this is basically occurs at what temperature? Room temperature. And a very few electrons only pass from valence band to which band? Conduction band. Now basically what happened when this semiconductor, okay, like we have taken the example of silicon, okay, at room temperature is connected to an electric field. Means when an electric field is applied, electric field applied means when this semiconductor is connected to a cell or battery, because cell or battery supply the electric field. So what happened under this case? The few electrons present in the conduction band, see, few electrons already present in the conduction band at room temperature, acquire even additional energy to move into the unoccupied level within the same band. That means they can go to the next higher level of the same band, conduction band. Similarly, few electrons present in the valence band, that means this band, moved to the few available unoccupied space in the same band. That means when electron will move from valence band to conduction band, there is some space will be created, okay, but under the presence of electric field, the electrons which are already in the conduction band can even move to the unoccupied level of this conduction band by getting some extra additional energy. Whereas very few of the electrons in the valence band can even move from this valence band to the unoccupied level of the same band. So this makes the conduction of current when this semiconductor is connected to a cell or battery. That means they conduct electricity. So due to this, the semiconductor has a very small conductivity. So under this condition, as you can see that there is a very limited flow of current takes place across the semiconductor, and due to this reason the semiconductor has very small conductivity that can occur at room temperature, and whose value lies in the range of 10 to the power 4 to 10 to the minus 6 ohm per meter. That means this range of conductivity is very less. But this conductivity which can occur by the semiconductor is only at what temperature? Room temperature. But the same semiconductor, if you take at a very low temperature, even less than room temperature, then that semiconductor does not even conduct electricity, because there will be no electrons present in the conduction band. Okay, no electron present in the what band? Conduction band. So this is the energy band diagram of semiconductor. Similarly, we can do now the energy band diagram for insulator. Now children, you know that insulator are those substances whose conductivity is very negligible and resistivity is very high. Okay. Now there are many examples of insulator, okay, which does not conduct electricity. Okay. Now this conductivity, the insulator energy band diagram of insulator can be also expressed in a similar manner like we have done for semiconductor. Now there is a conduction band and there is a valence band, but in case of insulator, there is a large energy gap between conduction band and valence band. Now basically if you see, the energy gap between the conduction band and valence band will be greater than 3 electron volt. So if the energy gap between conduction band and valence band is greater than 3 electron volts, that means that substance, a material is simply called as what? Insulator. Because under this case, what happened? The electrons which are present in the valence band are completely filled, where a conduction band is completely empty, and no electron can go from valence band to what band? Conduction band. Okay, due to large energy gap, the electron cannot move from valence band to what band? Conduction band. That's why the valence band in insulator is completely filled, while the conduction band is completely empty. Okay, now there are many examples of insulator, but I'll take the example of one of the insulator, and this is one of the hardest substance, and diamond. Let me draw that energy band diagram of diamond. Okay, so in case of diamond, the conduction band and valence band have a large energy gap. Okay, have a large what? Energy gap. This is valence band, and this energy gap between valence band and conduction band is approximately how much? 7 electron volt. So energy gap between valence band and conduction band in case of diamond, this is the energy band diagram. Okay, this is energy band diagram of what? Diamond. And diamond is one of the substance made up of carbon. Okay, so the energy band diagram of diamond as an insulator, okay, is very large, which is almost 7 electron volt. That's why diamond is one of the hardest substance and does not conduct electricity at all. Now this energy gap of 7 electron volt says that at least this 7 electron volt, okay, energy must be provided to an electron in the diamond crystal in order to enter from valence band to which band? Conduction band. Okay, valence band to which band? Conduction band. That's why in case of diamond, even at room temperature as one of the insulator, okay, valence electron present already in the valence band do not have what? Enough thermal energies to cross this 7 electron volt energy gap into the which band? Conduction band. Okay, into the what band? Conduction band. That's why in the presence of electric field, even if you connect this with the electric field, if you connect with the cell of battery, the electron in the valence band would not accept energy to move within the band, okay, and goes to the which band? Conduction band. So this is basically the case of insulator where they does not conduct what? Electricity. So no conduction of current takes place in case of insulator because of large energy gap. Like diamond cannot conduct electricity because of large energy gap. So that even if you connect with this with the electric field, the electron cannot go from valence band to which band? Conduction band. That's why in case of insulator, remember this, valence band is completely filled, whereas conduction is completely empty, even at what temperature? Room temperature. And even if you increase the temperature also, okay, you cannot even cross that energy gap, okay, to move from valence band to conduction band. That's why a normal insulator, okay, or the insulator at room temperature even does not conduct what? Electricity. Okay, so because of large energy gap takes place between the valence band and what band? Conduction band. So these are the energy band diagram of insulator and semiconductor. Due to this, the conductivity, so let me just write, the conductivity of insulator is extremely small. Okay, insulator has extremely small conductivity. Insulators, okay, have extremely small what? Conductivity. So that means almost there is no conductivity, I can say like that also, but they have very extremely small conductivity which can be in the range of what? Which can be in the range of, which can be in the range of 10 to the power minus 11, okay, per ohm per meter to 10 to the power minus 19 per ohm per meter. So that means this is the conductivity of what? Insulator. Means with this conductivity almost the insulator does not conduct electricity at all. Okay, and no electrons are available in the conduction band to conduct what? Electricity, even at what temperature? Room temperature. So this is the detailed explanation of the energy band diagram of both semiconductor and insulator.